Hello, and welcome to Module 2 of Advanced Topics in Healthcare Analysis. In this module, we are going to learn the basics of epidemiology. Understanding the application of epidemiological techniques will help you mine healthcare data for a wealth of information. In this module, we will cover what epidemiology is and the measures that are used in it. We'll talk about ways to analyze data using epidemiological techniques, and we'll talk about how understanding the causes and effects of different diseases can have an effect on keeping patients healthy. In order to get a good understanding about what epidemiology is, you need to understand two basic definitions. The first is epidemiology, which means the study of the distribution and determinants of health-related states or events in specified populations, and the application of this study to the control of health problems. A good understanding of how these ideas are measured can greatly assist not only in determining who may have what health issues, but can also assist in planning for treatment. The second definition that is key to understanding epidemiology and the role that it plays in the larger healthcare field is the definition of disease itself. We all have an idea of what disease may mean, but we will use the following definition. Disease is a bodily dysfunction, usually one that can be described by a diagnostic label. This term is also used to describe other common health issues such as death, disability, illness, or sickness. The idea behind epidemiology is that the data that we have collected around both health issues and our population can together tell us many interesting things about the health issues in the population we are working with. Some of the most well-known diseases of long ago were all virtually eliminated through the use of epidemiological principles. Scurvy was studied by James Lind in 1753 among British sailors returning from long sea voyages. He had noticed that some of these sailors developed scurvy and others did not. After synthesizing many hypotheses, such as sea climate and ship condition, he decided to investigate diet by running an experiment. The results of his experiment showed that citrus fruits were able to prevent scurvy. This was verified in 1928 when vitamin C deficiencies were shown to be the cause of scurvy. Another disease that has been recently making headlines is smallpox. Edward Jenner's observations of those who worked with cows being seemingly immune to smallpox and those not around cows needing a vaccination using the actual smallpox virus led to experiments in the 1790s that showed inoculation with cowpox acted as a preventative against smallpox. As a result of his observations and experiments, Jenner was able to predict the elimination of smallpox over 200 years ago. It is these type of techniques that allow epidemiology to have such widespread applicability. Good data mining, when combined with good observation, can lead to a very robust, if unexpected, conclusions. So then, how can epidemiology be used in the modern world? Not only can epidemiology be used to determine the causes of specific outbreaks of illness, it can be used to help define the characteristics of a particular patient population and which of those characteristics may be the most prevalent. It can be used to help you identify what types of procedures will be most needed in the next few years in order to help plan for future staffing or clinical needs. It can help you understand who your patient population is now and what can be expected of them in the future with regard to care needs. It helps to describe the health status of existing populations. It helps to explain the cause of certain diseases and predict the occurrence of disease. It also helps to understand what is needed to control the distribution of disease. By now, you should begin to see why understanding epidemiology and knowing its techniques are important to your understanding of the data gathered in healthcare. Epidemiology uses terms that are common in the medical world, such as incidence rates, prevalence of disease or symptoms, and mortality rates. We've all heard these terms before, but how many people actually know what they refer to? Understanding exactly what they mean and how to calculate them will allow you to use the data you have available to help you answer the earlier questions and explain your answers in a common language. This leads to a better understanding of the current situation and what will need to be done to ensure a high level of service in the future. Of course, like any good data analysis technique, epidemiology measures things and then makes inferences about those measurements. In order to have an understanding of what you need to measure to apply epidemiological techniques, we're going to talk next about variables, populations, and risks. Without a good understanding of what these means in the epidemiological sense, you will have a hard time moving forward in your analysis. In any scientific discipline, in order to determine if one thing is different from another, you need to look at variables. The same is true in epidemiology. By looking at a single variable or multiple variables, you begin to move down through the data mining process we talked about last week. To ensure that your variables can assist you in creating an accurate picture of health data, you need to check to see if they meet a few specific requirements. The first is that the variable should have an impact on health status both in an individual and in a population. It should be able to be accurately measured. It needs to be able to differentiate between populations by looking at pattern of disease or health status. It should also be able to differentiate between populations using some underlying characteristic that is known to be relevant to health status, such as income, childhood circumstances, genetic inheritance, or specific behavior related to health. Finally, it needs to be able to assist you in generating testable hypotheses and help to develop policies around healthcare, help to plan for delivery of care, or help to prevent and control disease. This may sound like a tall order, but as we continue with this module and with this course, you'll be able to see that these types of variables are everywhere. One of the basic units used in measuring epidemiological variables is population. If you think about it, humans have an inherent need to be recognized as a part of a social group. One of the harshest punishments for most people is to be isolated from all others in their group or society. The study of populations and how disease interacts with those in a population is what makes epidemiology different from other health sciences. An epidemiological study must be done on a population, not on an individual. The population may be very large, such as thousands or millions of people, or it may be small, such as 5, 10, or even 20 people. You may wonder, why does epidemiology focus on the population rather than the individual? The goal of epidemiology is to look at the health experiences of individuals and use that information to generalize those experiences to the population the individual belongs to. In order to accomplish this, epidemiology seeks to answer three main questions. 1. How does the pattern of this disease vary over time in this population? 2. How does the place in which this population lives affect the disease pattern? And 3. How do the personal characteristics of the people in this population affect the disease pattern? By answering these three questions, or variations of them, you can gain a much better understanding of both the effects of past experiences and how the disease patterns may affect the future. This can help in understanding an unexplained upswing in a particular symptom or disease is presenting in your clinic, and can also help to predict what types of planning efforts will need to take place as changes in the population being served occur. The conclusions that you draw from your answers to these questions can help you to make causal linkages for a population. For example, on a population level, there is a definite link between smoking and lung cancer. This conclusion, however, cannot predict whether or not a specific person will have lung cancer as a direct result from smoking. It can, however, help to give a prediction of the possibility that an individual will have lung cancer as a result of smoking. In order to understand the population you are investigating, you need to know whether the population is heterogeneous or homogeneous with regards to its exposure to particular disease factors. If you are investigating the effects of smoking and the entire population you are looking at smokes the same amount every day, you can't say for certain that lung cancer in the population is caused by smoking. This is because the population is homogeneous. In order to make a causal link between smoking and lung cancer, you need to find a population that is heterogeneous or has differences among its individuals in certain aspects. In this example, smoking. One of the challenges with dealing with things on a population level is understanding the differences between a sick population and a sick individual. An example that might help understand this difference is to look at another measure that is well known, the body mass index, or BMI. We know that in general, the U.S. adult population is considered overweight. With the BMI scale, overweight is the range between 25 and 29.9. This conclusion was reached after looking at the results of thousands of people. As a population, the U.S. can be considered sick. Now, if we look at the general population of India using the same BMI measures, the majority of the adult population would be considered normal body weight, or having a BMI between 18.5 and 24.9. If you were a person who has a BMI of 26, and we compare you to the general population, if you were in the U.S., you would be considered among the average adults, and if you were in India, you would be considered an outlier. This example points out why you need to make sure you are choosing the appropriate information to use and the right variables to look at when you're mining data to help answer a particular question. You need to know very specifically what is being asked, as the same information can give multiple answers when looked at from different angles. It may be that a variable measured at the individual level may not give you a true picture of the overall population, and vice versa. To ensure that you are choosing correctly, you need to understand the demographics of the population you are interested in. This could be anything pertaining to a population: births and deaths, marriages and migration, or relocation. Knowing the demographic characteristics of the population will help you to draw conclusions as part of your analysis. It can help you determine who may have a higher risk of obesity or high blood pressure. It can help you figure out if a clinic may need to expand its services within the next 5 years. It can help you estimate how many flu vaccinations need to be ordered this season. In contrast, without knowing the demographics of the population, you can't say whether or not a disease is occurring at a higher than normal rate or decrease it to the point of being under control. Whatever conclusions you draw from your analysis, if you know the demographics of your population, you can then apply those conclusions to a similar population located elsewhere. This is the key concept. Understanding the population's characteristics will allow findings to be shared and applied to other locations with similar populations. Once you have an understanding of the population, you can start to use this information to answer questions. These might be about the frequency of the disease's occurrences, such as are cases increasing or decreasing, what is showing up the most, who is it affecting the most. You can begin to determine what the cause may be for a particular change and why that change is occurring. You may need to provide information or recommendations on how to prevent the control the problem, or even create a way to determine if controls put in place are actually working. Once you have a good understanding of the population you are looking at, you can begin to explore different risks that may apply to that population. Let's start out by making sure we are all on the same page when it comes to term definitions. In the general sense, risk is the possibility of suffering some sort of harm or danger. That is what most people think about when they think of the term risk. In epidemiology, the meaning of risk is a little bit different. In this sense, the term risk is referring to the likelihood or probability of dying, developing a disease, or disease precursors. It is technically a proportion, so it has a value between 0 and 1. This is similar yet different from the more common definition. The reason for the difference from the epidemiological standpoint is that epidemiology's main interest is in the interaction between the probability of disease and all of the factors that go into influencing the risk level. This leads to our next term, risk factor. Again, in general, everyday terms, risk factor is usually meant to be something that increases the level of harm or danger that one may encounter. Again, in epidemiology, the meaning is slightly different. Usually, the term risk factor leads to thoughts of causes of risks. For epidemiology, risk factor can be considered to be a factor that is associated with an increase in the probability of an adverse outcome, but it's not necessarily a causal factor. Now comes the main question we are trying to answer with epidemiological techniques. In what quantity does the disease occur in a population, and how does this compare with other populations? As you can see, without understanding exactly what some of these terms means, answering the big questions will be that much more difficult. Next, let's do a quick review of some measurement terms. A count is a simple number of cases, for example, the number of patients seen for ear infections in 2008. A rate is the fraction that describes the amount of disease or health events occurring per unit of time in a specified population. For example, the 2010 lung cancer mortality rate for a certain hospital. A ratio is a fraction where one number is divided by another, usually unrelated. This could be something along the lines of 1 chicken for every pot, 1 order of fries for every burger sold, or even 4 nurses for every hospital. Proportions are a specific type of ratio that contain the numerator in the denominator. For example, the proportion of 10th graders who report ever using their public library is the number of 9th graders who reported using the library divided by all 9th graders in 1999. Often, proportions are shown as percentages. In this next section, we are going to discuss two main measures in epidemiology: Virtually all other measures hinge on these two. These two measures are incidence and incidence rates and prevalence rates. Let's start out with giving a brief definition of each of these measures, and then in the next few slides, we'll walk through exactly how to calculate them. Incidence looks at the number of new cases in a particular population over a period of time. Prevalence looks at the total number of cases of a particular population at a defined point in time. In both measures, the equation consists of a numerator and a denominator. The numerator is generally the number of cases, and the population is the denominator. The key thing to understand in these definitions is what type of cases are looked at by each and during what time period. Incidence only looks at new cases, while prevalence looks at all cases. Incidence looks at the situation over a period of time. Prevalence looks at the situation at a single point in time. Without understanding this difference, understanding how to calculate each will be very challenging. In addition to understanding the difference between incidence and prevalence, it is also important that you know the difference between a rate and a ratio. In your past experience, you may have heard or even used these two terms interchangeably. In epidemiology, they represent different ideas, so you need to be able to distinguish between them. Let's start out with what a ratio it is. It is usually thought of as any number in relation to another. Thus, a rate that compares the numerator to the denominator can be thought of as a basic ratio. In epidemiology, there's a slight difference in meaning between these two terms. A rate is used in the situation where the numerator and denominator have different qualities, such as deaths in population. A ratio is used in the situation where the numerator is part of the denominator, such as deaths due to one cause or deaths due to all causes. In epidemiology, we are looking at disease frequency. This is generally measured and portrayed using incidence rates and/or the prevalence rate. One of the biggest reasons to understand the proper use of these terms is that using them in an incorrect context can have a great impact on how the level of risk may be perceived. Additionally, changes in usage of these terms can affect how measures of frequency are used to prioritize effects. We'll start a discussion around measures with prevalence. You may have noticed that the title of this slide is prevalence rate, not prevalence. This is because the prevalence, without a rate, is strictly the count of existing cases. It doesn't relate to anything. The prevalence rate tells you the number of new cases is related to the population studied. In order to calculate the prevalence rate, you need to find the number of existing cases at a particular point in time. To calculate the prevalence rate, you then take the number of existing cases divided by the size of the population at a specific point in time. In order for your calculation to be valid, you need to know your time period. This could be a specific date, such as the prevalence of CHD in Montana on September 2nd, 2001, or it can be an age or age group, such as the prevalence of urinary tract infections in women ages 18 to 21. It can also be an interval of time, for example, the prevalence of depression among veterans 6 months after returning from a tour of duty. As we learned earlier today, prevalence rate Sorry about that. As we learned earlier today, prevalence rate includes both new and old cases. If not understood correctly, it can have a great effect on how it is interpreted. Prevalence rate is a function of both the occurrence of new disease and the duration of that disease. This means that rare diseases or conditions can have a high prevalence rate if the duration is long. For example, PKU is a disease where an individual does not have the enzymes needed to process certain amino acids. If it is detected early in life and a specific diet is maintained, people with this disease can live for a long time. If looked at over a long time span, the prevalence may be high for people having PKU, but the condition is still fairly rare. Alternatively, some common diseases can have a low prevalence rate if the duration is short. For example, fatal heart attacks may be relatively common, but the prevalence would be short due to the inherent length of the disease. This usage of both new and old cases can also be a limitation of the measure of prevalence rates. This is particularly so when you're trying to estimate a situation such as an epidemic. You need to have a baseline of existing cases before any new cases occur. In this sense, the prevalence rate wouldn't give you what you need. Another example would be to look at those who have pancreatic cancer. Most die within a year. If you are studying cases that have survived 4 to 5 years, you won't have a good representation of those cases that are newly diagnosed. Asking yourself if the cases that you are studying are representative of the population is a good check to make before finalizing your analysis. Now that we've talked a bit about what prevalence rate is, let's look at an example of how to calculate it. Our question is, what is the prevalence of disease in this population on August 1st, 2005? First, we need to look at the time period. Because prevalence looks at all cases, we need to count all cases before August 1st, 2005. In our diagram, there are 3 cases, B, C, and D, that meet this criteria. You may be asking, what about cases A and F? They occurred before August 1st. We don't count those cases as they started and finished before our specific time frame. So our numerator is 3 cases, B, C, and D. Next, we need to know our population count. At the top of the diagram, it says that this is showing a population of 1,000 people. This is our denominator. To calculate our prevalence rate, we divide 3 cases by 1,000 on August 1st, 2005. We have talked a bit about how to measure the situation of existing cases, old and new, over a specific time period. This is prevalence. How then do we measure the situation of looking at only new cases over a period of time? This calculation is called the cumulative incidence rate, or CIR. 2 big differences from the prevalence rate calculation should pop out to you when looking at this new equation. First, the numerator is only looking at new cases within the population. Second, the denominator is looking at the number of people who are at risk at the start of the time period. This may not seem like a big difference, but it has large effects. In order to calculate the cumulative incidence rate, you need to have a specific time period, say a 1-year CIR. This will give you an estimation of the average risk that a person in this population will develop the disease during this specific time period. There are a few additional things you need to know in order to make an accurate calculation of the CIR. You need to have the assumption that the entire population observed was at risk for developing the disease during the time period. You also need to assume the risk is evenly distributed over that time period. This is known as constant risk. If the second assumption cannot be held to be true, you can then break up the time period into smaller ones, calculate the CIR for those smaller time periods, and add those rates up. You also need to know if this type of disease is one that confers immunity on those who have contracted it. If this is the case, once a person has the disease, they will not get it again. An example of this is measles. The alternative scenario is that the person has the disease, and once it is resolved, they are at risk again. Finally, you need to know if this disease is fatal. Let's walk through an example of calculating the CIR for our population for the year 2005. In this example, we'll assume we know this disease gives immunity to those individuals who have had the disease before. If we know this, we can say that the person who was case F would not be at risk during 2005, as they have already had the disease. Because the CIR only looks at new cases during this specific time period, persons that are cases A and C would not be considered to be at risk in 2005, as they are currently experiencing the disease. So for our numerator, we need to look at the cases that were new during 2005. Looking at our diagram, these are cases B, D, and E. This means our numerator will be 3. Here's where you need to pay attention to the data. For the denominator, we will start with our population of 1,000. But for 2005, we have 3 people who don't count as being at risk because they have either already had the disease or currently have it. These are A, C, and F. This means that our denominator for 2005 will be our 1,000 in the original population minus the 3 ineligible people for a denominator of 997. Thus, our CIR for 2005 would be 3 divided by 997. One of the problems that can arise when you're looking to calculate a CIR is that people, fortunately or unfortunately, do not like to stay put. This means that the population you started with at the beginning of your time period may be different than the population at the end of the time period. People may move during the course of the study, so you may have a larger or smaller population than you started with. In talking about the CIR, it was noted that this calculation produces an estimate. This is because to assume that the population is the same throughout a study period may result in a biased output. There are incidences in which an estimate is exactly what is needed, and this is what the CIR is for. For those times when you need a more accurate understanding of risk, you can use a standard incident rate calculation. So far, we've talked about the situation for looking at all cases of disease in a population, or the prevalence rate, and the situation for looking at new cases during a specific time period, the cumulative incidence rate. But what do we do when we want to look at new cases over time in general? In equation terms, we want to look at new cases in a population considered to be at risk. More specifically, we are interested in new cases during the time period that the people in the population were at risk. In order to measure incidence properly and calculate an incidence rate, you need to know 4 things: the number of new cases, the population at risk, the time period, and the place of study. In the case of our population, not everyone may stay put for the duration of your study. This means we can't count them as being at risk for the entire time period. When we calculated our CIR, we removed those people who already had the disease or currently had the disease, and assume everyone else stayed put in 2005. But what if they didn't? How do we account for the fact that our denominator changed mid-year? The best way to handle this is to use something called person time of observation. Person time of observation lets you count only that time period that the person was at risk in your population. To better understand this idea, let's walk through an example of how to find the person time of observation. First, let's start out by looking at a population that is fixed. We'll look at what happens over 5 years. For some context, let's look at a population of 6 patients who have been told that they are pre-diabetic. In order to hopefully prevent development into actual diabetes, they need to follow their provider's instructions and come back for visits. At the start of our observation period, year 0, all 6 patients are considered pre-diabetic and at risk for developing diabetes. During the course of the 5 years, some of the patients are able to reverse their diagnosis and are no longer considered to be diabetic. This means that they are no longer considered to be at risk for developing diabetes. Some patients are not able to reverse their diagnosis and continue on as pre-diabetic for the entire 5-year observation period. So, how do we count the population at risk? We count the number of years to the nearest half year that each person was considered to be at risk for developing diabetes. If we look at our diagram, this means that patient 1 was at risk for 2 years of the 5-year period. Patient 2 was at risk for all 5 years, and so on. Then we add all of the individual patients' years up to get the person time of observation. In this case, we add 2 plus 5 plus 1 plus 3.5 plus 5 plus 0.5 to get 17 person years of risk for this population. Because we are only looking at the actual time that each person spends at risk in our population, we can do the same thing with a dynamic population, or a population that moves. In this case, we can think of our population as those individuals coming into a clinic who are diagnosed as having pre-diabetes. Not all patients coming in may have this diagnosis at the beginning of our time period, but we can still use their risk to calculate the amount of risk. Here you can see patient 1 was not pre-diabetic at the beginning of the study period, but was diagnosed at year 0.5. This patient was able to eliminate their risk by year 2.5. This means that the total time spent by patient 1 at risk during our study period is 2 years. In order to calculate the person time of observation, we add up all the time that each patient was at risk just like before. This time, we would have 2 plus 2 plus 1 plus 3.5 plus 2.5 plus 0.5 for a total of 11.5 person years of risk for this population. Now that we know our dynamic population has 11.5 person years of risk, we can calculate our incidence rate. The person years of risk is our denominator. Remember, incidence rate uses new cases, not all cases in the numerator. This means by looking at our diagram, we would eliminate person 3 and person 5 from our numerator, as they have already been diagnosed when our study period began. So for our numerator, we have 4 people, and for the denominator, we have 11.5 person years. This makes our incidence rate 4 people for every 11.5 person years of risk. As you might imagine, calculating person years really only makes sense for small populations. What if you were trying to find the incidence rate for an entire city? You could try and calculate each individual's person years, but you'd probably make yourself a bit nuts. Instead, you can use the CIR rate calculation with your time period being a single year. Basically, you are assuming that everyone contributed 1 year to the amount of risk. You could also use a mid-year census count to act as the denominator. As populations get bigger, the changes in risk level that occur on an individual level get smaller, just due to the sheer size of the group. As always with good data analysis, you need to be able to explain what you chose to do and why. This helps explain what your results are showing and why you are working with the data in the manner that you are. Once you know how to calculate the basic measures of prevalence and incidence, you need to be able to use the information that they give you to begin looking for patterns. Part of finding patterns is knowing how to interpret things such as mortality rates and risk levels. These next few slides should give you a background in how to do just that. Now that you know how to calculate some of the basic measures in epidemiology, the next thing to understand is what type of patterns epidemiology helps you to understand. The 3 major areas that tend to show patterns in healthcare data are person, place, and time. Person looks at what kind of people get a particular disease. Place asks, is the disease common or rare, and what are the specific characteristics of those places. For time, we are looking at how the frequency of the disease changes over time and what factors tend to be associated with the disease. If we're looking at characteristics of people that can relate to a disease pattern, one characteristic that is commonly seen when looking at certain diseases is age. For example, if we look at the 2009 chart book put out by the CDC, it shows that in 2006, more people in the age group under 75 died from cardiovascular disease than those in the age group of under 35. Thus, one pattern that we can see is that age seems to affect death by cardiovascular disease. This same population shows us that mortality for heart disease in general was 53% higher in males than females. So gender can have a relationship with disease as well. Additionally, ethnicity can have a relationship, as in the well-known situation of certain ethnicities having a higher risk of sickle cell anemia. Other common person characteristics include socioeconomic status, education level, marital status, nutritional status, and behaviors. 2 of the most commonly used measures of pattern among the people aspect are mortality, the probability of death due to a specific cause, and morbidity, the proportion of a specific disease in a given population. Characteristics of place are usually some of the easiest to define. Things such as geographic factors and climate are fairly distinct. Geopolitical factors such as war or healthcare policy can also show a link to disease. You can also look at social factors and the physical environment and the biology it contains to determine a relationship with disease. In addition to understanding the characteristics of the person and the place, knowing the characteristics of time can often help to solve an epidemiological puzzle. For example, if you were looking at the prevalence of Lyme disease in the U.S. over the last 30 years, you would probably see a spike in cases around 1982 and 1983. This is due to the fact that the CDC started requiring reporting of Lyme's disease in 1982. You may see increases in certain diseases at certain times, such as seeing an increase in sunburn during the summer months. In contrast, some trends in disease occur over a long period of time. Another example of time influence on disease is that the incidence of lung cancer increased as the prevalence of smoking increased. This was not a sudden increase, but over the course of years. As one of the most widely known epidemiological measures, mortality is a key measure to understand. There are three different mortality rates that are differentiated among those who created them, but are generally not differentiated by the general public. This can be an issue as each of them represents wildly different measurements. The three mortality measures are crude, specific, and standardized mortality rates. A crude rate is a summary rate that is based on the actual number of disease cases relative to a defined population in a defined time period. A specific rate is a rate that is calculated using a subgroup of a population, such as age, gender, or risk profiles. A standardized rate, sometimes known as an adjusted rate, is a rate that has been manipulated to remove confounding effects when two or more different populations are compared to one another. To help make these different rates a bit clearer, let's look at an example. Here, you can see the population information for Australia and the Bahamas. This is their respective populations as of 2009, which was obtained from the website census.gov in the international section. The website also gives the number of deaths of all causes for that year. To calculate the crude mortality rate for each country, you would divide the number of deaths by the population of the country in mid-year. So for the Bahamas, you would divide 2,153 by 307,552, which equals 0.007. To get deaths per 100,000, a more commonly used and understandable rate, you simply multiply by 100,000. This results in the Bahamas having a crude mortality rate of 700 deaths per 100,000 population in the one-year time period for 2009. If we want to compare the two countries, it can be seen that even though Australia has a much higher total population, its crude mortality rate is the same as that of the Bahamas. An example of the specific rate is to look at the death rate when grouping by gender. The calculation is done the same way, but using the gender-specific numbers. So, to calculate the specific mortality rate for men, you would divide the number of male deaths by the total male population for that year. After doing this for both Australia and the Bahamas, we could see that in both countries, women have a slightly higher mortality rate overall than men. Now, one thing to remember is that the particular measure is not looking at lifespan. It is only looking at deaths from all causes. One question you might be asking yourself as you look at this chart is why don't the specific mortality rates add up to the crude mortality rate? This is because the crude mortality rate is a weighted average of the gender-specific rates, but the proportion of the population in each gender is different for each country. What about the standardized rate? To find the standardized rate, you would find the specific rate for each gender of each country and add those up to create a new combined rate. Then you multiply the new rate by each of the specific rates for each gender in each country. Finally, you sum all of the outputs for each country, sort of like calculating a grade when 3 exams are each a different percentage of the total grade. With that in mind, why might you want to use the 3 different mortality options? Well, the crude rate can be useful when you only want to look at the summary of diseases experiences in a total population. The specific rate gives you a more detailed breakdown by category groups. And the standardized rate can help you to compare groups that are similar. One caveat with the standardized rate is that it is really hypothetical and not an actual disease rate, only a comparison. Earlier in this module, we talked a bit about what risk is in epidemiology. It is the likelihood or probability that a particular individual will become diseased or die or develop disease precursors during a period of observation. To measure risk in a population, we can use the measures we just learned, incidence rates or mortality rates. If we want to compare the risk between populations, we can use a ratio of risks. To look at this, you need to know that in general, we want to look at 2 different groups, exposed and unexposed. Then we want to know who developed the disease. That sounds simple, right? A visual way to look at this is to create a 2x2 table, such as this table on the slide. In our table, the letters in each box represent the number of people who meet that criteria. Thus, people who are in the A group were exposed to a risk factor and developed the disease. N in this table is the total of the entire population, or A plus B plus C plus D. One of the big questions that is often asked when looking at diseases is, does exposure cause a disease? This is known as a relative risk. Using the 2 by 2 table, you can calculate the relative risk for different portions of your population. To calculate the relative risk for the exposed portion of the population, you would divide the number of people exposed and developed disease by the total of all people exposed. You can do the same calculation for those that were unexposed for the total population as well. Why would we want to calculate all those relative risk numbers? What can it really tell us? One thing that the numbers can tell us is whether or not there's excess risk. Excess risk is the amount of disease that is associated with a particular exposure. If you compare the occurrence of a disease among exposed and unexposed populations, you can determine if exposure is a cause of the disease. If this were the case, the excess risk would be the amount by which the disease would be reduced if the exposure were eliminated. To determine the level of excess risk, you need to use a risk ratio. To calculate a risk ratio, you use your 2 by 2 table to determine the relative risk of both the exposed, which is cell A divided by cells A plus B, and unexposed, which is cell C divided by cells C plus D. Then you divide the relative risk of the exposed by the relative risk of the unexposed. This gives you the risk ratio. In this situation, what does the result of your calculation tell you about whether exposure causes a disease? If the result of the equation is 1, there is no association between exposure and developing the disease. If the result is greater than 1, there is a positive association. And conversely, if the result is less than 1, there is a negative association. When thinking about the positive and negative association of the risk ratio, you can think of the difference in this way. If there is a positive association, the exposure to the risk factor causes the disease. If there is a negative association, the exposure to the risk factor would be considered a protective factor for the disease. In some cases, we want to not only know the risk ratio of the excess risk, we might also want to know the difference in risk. This is known as the attributable risk. In this situation, we want to know whether the incidence rate of a particular disease is attributable to a specific risk factor. We can set up a 2 by 2 table to calculate the incidence rates for the exposed, unexposed, and the developed disease versus didn't develop disease. Once we have that, we can then subtract out those that were unexposed and developed disease from those that were exposed and developed disease. The reason that we use the unexposed and developed disease rather than those who were unexposed and didn't develop disease is that we have to assume that even with no exposure to a particular risk factor, someone may have developed the disease. The amount of risk that is left over would be considered to be the excess risk for that particular risk factor. In slight contrast to the attributable risk, we also have the population attributable risk. This measure is one that can be used to help determine where, how, and when resources should be allocated. To find the population attributable risk, you first find the cumulative incidence rate of the entire population for this particular disease. Once you have that, you then calculate the incidence rate for the population who are unexposed. This gives you the population attributable risk. This is great, but what is it telling you? The population attributable risk tells you the incidence of the disease in the population due to the particular risk factor. This is what can help you allocate your resources appropriately. Another question that gets asked when talking about the propensity for getting a disease is, what are the odds? So what exactly are odds? The definition of odds is that they are a ratio giving you a probability. Odds can be the probability that an event will occur or the probability that an event will not occur. It can also be the ratio of the probability that something is to the probability that it is not so. To figure out odds ratios, we need to turn to our friend, the 2 by 2 table. First, let's look at the odds of getting a disease. For those who exposed to the risk factor, the odds of getting the disease is the ratio of the probability of developing the disease over the probability of not developing the disease. If we use our 2 by 2 table, we first need to find the probability of developing the disease if you're exposed. This is cell A divided by cell B. Here we are looking at those who are exposed and developed the disease compared to those who are unexposed and did not develop the disease. We can do the same for the unexposed. We find the probability of developing the disease if you're not exposed, or cell C divided by cell D, those who are not exposed and developed the disease, divided by those who were not exposed and did not develop the disease. Once we have these two numbers, to find the actual odds ratio, we divide the results from exposed by those from unexposed. This tells us what the probability is for developing a disease. Another question along those same lines is, if we know people are diseased, what are the odds that the disease was due to being exposed? We can calculate this in a similar manner. To answer this question, we need to think of it in looking at those who are exposed. So, we start out by finding the probability of being exposed in those that have the disease. Then we find the probability of not having the disease and being exposed. Again, just like above, we can calculate the exposure odds ratio, but by dividing the first number by the second. This gives us a probability that developing a disease is due to exposure to a risk factor. These equations may seem to run together, and we have talked about a lot today, but the key to knowing which equation to use is understanding what the question you are asking is. So, if you want to know the number of existing cases at a particular point in time, use the prevalence rate. If you are only interested in new cases over a period of time, use the cumulative incidence rate. If you are interested in new cases during the time period that the people in the population were at risk, use the incidence rate. If you want a summary death rate that is based on the actual number of disease cases relative to a defined population in a defined time period, use the crude mortality rate. If you want the specific death rate that is calculated using a subgroup of the population, use the specific mortality rate. A death rate that removes confounding effects when two or more different populations are compared is the standardized mortality rate. To compare risk between populations, use the relative risk. The amount of disease that is associated with a particular exposure is known as the excess risk. The incidence rate of a particular disease that is attributable to a specific risk factor is the attributable risk. The incidence of the disease in a population due to a particular risk factor is the population attributable risk. The odds of getting a disease is the disease odds ratio, and the odds that the disease was due to being exposed is the exposure odds ratio. Hopefully, these calculations will help you to better understand and analyze healthcare data that you encounter during your work.